I think that's what really long they think.
So last, so last lecture, we started a new layer of our system, which is the architecture layer, right? And we said our main goal, and again, this is very, very important to keep in mind, right? What are we doing in these lectures? If you remember at this line, we started by writing this equation, right? What equation I'm referring to? WCET is composed of WCCT, which is the computation time on core, where all the scheduling is concerned about, plus, yeah, some interference term, which is the number of requests you send to a resource, multiplied by the worst case delay or latency of a single request. And we said, what are we doing in this set of lectures is we take every shared resource and we add a term for it in the overall execution time, simply to calculate what is the worst case delay that a single request will suffer, right? We do this for the interconnect, we do it for caches, and we do it for main memory, okay? So this lecture, we are continuing the interconnect, and then next lecture we'll start the caches and then the main memory afterwards. And we took some sort of an architecture brief background about interconnects, bus architectures, crossbars, network on a chip, which is a network on a chip can be of a form of a ring, a mesh, and some other stuff. And then we delved into what is important for us in real time, which is deriving a worst case latency using predictable arbiters, right? And we have introduced some of the arbiters, and we even solved some of the questions related to the arbiters. We said TDM, round robin, and work conserving TDM. These are the three that we cover, right? And then we had the example. We said it's best really to draw with an example. We had this example where we said at time 0, there are these requests that are arriving, which is C1, C2, C4. C4 means 2 requests from C4, then C5 and 6. And then sometime later on, you will receive a request from C3. In an exam, for example, what I will tell you is, this is a sequence of arrival of the requests. At time 0, and I give you this sequence, and then at time, assuming one slot is 10 cycles, and I will give you that, for example, in a question, and say maybe at 22, C3 arrives. Good. And we said we want to schedule this using different schedules we covered. Starting by TDM, baseline TDM. We said TDM, its main characteristic is static, and it divides time into slots, gives a slot for every core, and at the beginning of the slot, just very blindly looking the core assigned to this slot. If you have something, I schedule. If I don't have something, I remain idle, right? Very straightforward. So if we solve with TDM for this sequence, we say at time 0, do I have anything from core 1 for this core 1 slot? The answer is yes. So you schedule core 1 slot. Then after you are done with C1, you go to your lookup table and look for the next core. It's core 2. Does core 2 have something? The answer is yes. So basically you schedule C2. Now at the beginning of C3, this is C3 slot. Does C3 have something? No. At the beginning of the slot, no. What do? You remain idle. You waste the slot, which is one of the disadvantages of TDM. So I waste the slot, and then at the beginning of C4, C4 has a request, so I serve it. C5 has a request, I serve it. C6 has a request, I serve it. Now I go back again after I'm done from C1 to C6. Simply it's a period, right? It's a periodic arbiter. So you go back to C1. C1 does not have any request because I already served with C1, so it's done. C2 does not have anything, wasted. At the beginning of C3, does C3 have something in the queue? Yes, there is a request arrived here and it's not serviced at all, right? So C3 has a request, I serve it. C4, I serve, right? Now, if you think about C3, it's suffering really the worst case. If you count the number of slots or cycles that C3 suffers. Yeah, just give me, sorry, one second, then I will take this. So C3 arrives at the beginning of this slot, and then it gets serviced here. So if we say one slot is S, or let's say it's 10 cycles, and I arrive at time 21, what is the total delay C3 For arbitration, you arrive at 21, but you get serviced at, this is 10, 20, 30, 40, 50, 60, 70, 80, right? So you suffer 60 minus 1, which is 59, right? So you suffer 59 slots. If we ignore the 1, we say that 60, which is simply 6 S slots. What is 6? Is the number of cores, right? So you suffer in general N S arbitration delay slots. Then I also take my access time, which is another S, right? That's why we said the total worst case delay, the OCD of TDM, is in fact N plus 1 S. NS for the arbitration and S for the access time. Good? Yeah.
Cycle 21. We are speaking about the delay for C1, right?
No. 21, we're talking about the delay of C3 then. You arrive at a certain cycle, but you don't get access to the bus up until another cycle. So all this time you are waiting.
Yes. So we're saying 60 minus 159 second delay.
Yeah, not seconds, like cycles, but yes, it's a delay. Yes, an arbitration delay.
And if it arrive at cycle 20, then like
you will get serviced immediately because you are at the beginning of the slot. So if you arrive at 20, then this slot will be dedicated to you because this is C3 slot. That's exactly what happened for C1. C1 arrived at time 0, it gets serviced now. So it does not suffer any arbitration delay. It suffers only the access time delay. So this is a best case scenario. Arbitration delay is 0, and the access, you always suffer the access time because you need to access the bus, right? So delay 0, this is arbitration delay NS. So this is best case, this is worst case.
I don't know. Why is it not labeled? Like, does that have a meaning?
I'm not sure if I understand what you say.
Just blue.
I'm just using color coding for simply assigning certain slots to cores, right? Just to make it visual for you, right? But the key idea is you start from C1 up to C6 and then you start again.
No, I mean, but like 3 of them are missing the color. Like, why is this one missing? Why is it empty?
It's empty because this slot remains idle. It's a reflection of TDM at the beginning of the slot. Does not have anything to serve from C3, so it just leaves it empty. Okay.
So here the delay is 80 minus 20, minus 1 also. Right?
Yeah, but we just ignored the 1, right?
Okay, so it will be 60. That's the same as N times S exactly.
Exact, which is the worst case. Okay.
So are we assuming that like every C needs exactly 10 seconds?
Yeah, that's an excellent question. That's the case here. We're assuming the interconnect has a fixed time to transfer data. Once every request gets access to the bus, it consumes S times or 10 time cycles in this example. Yeah. Generally, that might not be true, but for TDM, because you have to dedicate slots, and this is in fact one of the disadvantages of TDM, because I have to dedicate slots, and all the slots must have fixed width. In round robin, it's different because you start and you finish, so there is no concept of slotting, right? In round robin, yeah.
When you add plus S to N times S, this added access time for core 3.
For the request under, we call this the request under analysis, the one that you are concerned about.
So this is the delay for core 3 request or the core itself?
It's the request for core 3 through the bus. Yeah. Okay. So this is for TDM. And then we said a slight variation of TDM, which is improving performance, is work conserving TDM. In work conserving TDM, I don't waste an idle slot. I look into what is next in my lookup table, pick up the next core and assign it to it. So if we solve the same problem using work conserving TDM, at time 0, this is C1 slot, it has a request, so I serve it. C2, the same thing. The main difference is at the beginning of C3 slot, does C3 have a request? The answer is no. In work conserving, I don't waste it. I look into the core next, which is C4. Does C4 have a request? The answer is yes, so I serve it. But in work conserving TDM, we said the main feature is still TDM. So C4 does not lose its own main slot because it's against a lookup table. You go back again to C4, it has a slot. Does it have another request? The answer is yes. So you also serve it. And then C5, C6, and then C3. You see here that the advantage of work conserving TDM is that you are really saving 3 slots. So it's better in terms of performance. What about worst case? The worst case remains the same, right? The worst case does not really change. Oh.
I'm very confused. Like work conserving TDM, it's like taking from the queue.
serving TDM is you don't keep a slot idle if you have a core with a pending request. In TDM here, we left this slot empty. So there are 10 cycles on the bus that really is doing nothing, right? Because C3 does not have anything. Here we used it to serve C4.
C4 was already there.
Yeah, because it had a pending request. So we serve it. Okay. Questions? Good enough?
I'm not sure how it looked like in the exam, because I didn't understand the slide the way this was spending.
We will solve a couple of questions after we're done with the concept, but I think for lecture, let's focus on understanding the concept. And then for round robin, last time we said you can have two different implementations of round robin, right? You can really assume you always arbitrate among all the cores, whether they have pending requests or not, or you only consider requests with pending requests. So round robin, how do we implement round robin in reality? Is through a cyclic buffer, right? This is what any operating system will do or hardware will do. There is a queue that is cyclic. And once you serve a core, you put it back to the end of the queue, right? So for this one, I will take an empty slide and solve it with you because it's very important to understand that. So in one round robin implementation, we say I always put, so here we have 6 cores, right? So in one implementation, you say those 6 cores will always be inserted to the buffer. Whether you have a pending request or not, I don't care. So I put in C1, C2, C3, C4, C5, C6. And then I take every core from the top of the queue, check. If you have a request, I serve you and I put it back in the queue. If you don't have a request, I don't serve you, but I also put you back. But you always remain in the queue. That's one implementation of round robin. Another implementation for round robin is you only arbitrate among cores that already have pending requests. So for example, if C3 in our example does not have any request, I will not even put it in the queue, right? So I will say at the beginning, I have C1, C2, C3, C4, C5, and C6, for example. Once C3 have a request arriving, I will put it in the queue. So now let's solve the example we have to see how it does really work. At time 0, I had requests from core 1, core 2, core 4 had 2 requests. Do they arrive back to back? Yeah. And then C5. And then C6, right? This is at time 0. So how the queue looks like at time 0, I will look into the queue here. Well, at the beginning, for this implementation, all the cores are already in the queue, as we said, right? So I look into the queue at time 0, C1. Does C1 have a request? The answer is yes. So I serve C1. And once I'm done with C1, C1 will go back to the end of the queue. And the queue will be like C2, C3, C4, C5, C6, and then C1 is at the end now, right? You guys are good? Have questions? So then C2 at the beginning of the slot. Do we have a request for C2? The answer is yes. So basically I take it out of the queue and serve it and put C2 back. So here C2 will be at the end. So C3, C4, C5, C6, C1, C2. Now C3, does it have a request? No. So I take it, put it back, and I don't serve anything from C3. And I look into the core next. What is the core next? C4. C4 has a request, so I serve it. And then at the end here, I will have C5, C6, C1, 2, 3, and 4. Now, who is in the top? It's C5, so I serve it. And then C6, I will serve it. At the end of C6, you see that we go back to our cyclic queue back again from C1 to C6, right? Now, C1 does not have anything. C2 does not have anything. C3 is the first one to have something, so I serve C3. And then C4 has a request, so I serve it. Cool. So that's this implementation of round robin. The key aspect of this implementation is you always arbitrate among all requests, whether they are all cores, whether they have requests or not. Okay. Now, second implementation is trying to be more efficient. You say, oh, why, for example, C3 here lost its round in the queue without really leveraging it because it doesn't have anything. So what you say is, I only put the core in the cyclic queue if it has a pending request. If it does not have a pending request, I don't even consider it. Okay. So how does it work? Like at the beginning, I receive the request from C1, so I push it to the queue. C2, I push it to the queue. Yeah, mom, just are you asking about this one or the new one? Yep. At the beginning, the queue is empty.
Yeah.
Requests arrive in that sequence. C1 had a request that is arriving at time 0, so I push it to the cyclic queue. And then C2, I push it. C4, I push it. Then C5. And then C6.
Yeah.
C3 will not be in the queue
Because it
because it does not have anything yet. That's different than this implementation. This implementation is always using all the queues in the cyclic fashion, whether they have something or not.
So the first implementation is a static one and the other one is more than.
You cannot say it's static. This round robin is generally dynamic, but it's different on pushing cores or which cores you consider. Usually we call this the pool of arbitration. Which cores you consider for arbitration.
One has a fixed pool and the other.
Exactly. It changes based on arrival. That's correct. Yeah.
CPU, like,
Hmm?
what is it?
It's a CPU.
Why do we call it a book?
Why we call it CPU?
Because I see those as like 8-core laptop. Why don't you just tell me 8 CPU laptop?
In reality, there is a subtle difference between cores and CPUs. A CPU can be composed of multiple cores. A CPU has a general meaning than a core, right? So a core is your pure computation unit. The CPU has some other elements into it, right? But that's a difference that's usually overlooked in marketing and even in some of the books. So you can say a core is equivalent to a CPU to some extent. So why we give it two different names? Again, for the reason I told you, is that they are in reality they are a little bit different. But that's something orthogonal to the course. I wouldn't spend more time on it. Let's talk after the lecture if you're interested.
Like that, like why would I ever want the CPU to be idle?
In round robin, the CPU is not idle. In TDM, and put in mind that we're talking about an idle bus, not an idle CPU. The CPU might be doing computation. Here we are arbitrating for the bus, whether you access that bus at this time or not. Okay?
Like, why would I ever like TDM? Looks like a bad idea.
From a performance perspective, yes. From analyzability and predictability and composability, no. TDM is favored a lot, for example, in avionics, because it gives you a very static behavior that you can very easily analyze and reason about. So certification authorities like it a lot because it's you can really write formal analysis easily with TDM. Yeah, exactly. If something goes wrong, also how you can retrieve what is the error and that stuff. So static schedules, we gave this, and this is a very important trade-off for this course, right?
We both, like you said, compliance is better.
But can I finish the sentence first? So basically, it's something very important to understand in that course. There is always a trade-off between performance and predictability. We said at the beginning in lecture 0 and lecture 1, when we set the stage, is that if we talk about a very basic embedded system, 241 style of things, you don't care about performance. So you don't have a lot of challenges. It's very easy. No operating system, bare metal application running at very few hertz and no interference, no multi-core, nothing, right? So it's a very simple thing. But we said all the modern applications of embedded systems, if you go and work for industry, are starting becoming multi-core. You care about performance because you do perception, machine learning, machine vision. So we need performance. All of what we're discussing of the challenges in that course are in fact at the core of this challenge between performance and predictability. Now, why this is relevant to your question, Mohammed? Because you said, why I ever favor TDM? TDM takes one extreme side. It's great for predictability. It's bad for performance. Round robin is taking a middle ground. There are, in fact, more performance arbiters than round robin. So they are taking the other extreme, is that I'm very high performant, but really not very predictable, right? We give the example of first come, first serve and other stuff, right? So there's a spectrum of arbiters based on your use case. Now you wanted to add a follow-up in the middle?
So you was talking about compliance and like
Compliance is from a certification authority perspective. Like, how do you analyze your system? If you're static, it's easier to analyze. So this is why TDM might be favored there. Okay.
Why don't we just add flags every time it comes in?
Yeah, you can always ask why we don't, and there might be few implementations, right? There are a lot of variations based on the use case, but we're giving the titles and the general classes of work, right? And then implementations might be a little bit different, right? Any other question? Okay, so for this second version of round robin, again, I only push in cores to the queues if they have pending requests. Okay, so we pushed in C1, 3, C1, 2, 4, 5, 6 at the beginning, and then at the time of the arbitration, C1 is at the top, so I serve it. Then C2, so I serve it. C4, so I serve it. And then at this time here, C3 request arrived, right? If I remember correctly, C3 request arrives at the after, no, it arrives here. So what do I do at this time? I push in C3 in the queue. How the queue looks like at the beginning of this slot after I serve it C2? It will be C4, 5, 6, right? At this point, it's 4, 5, 6 because I already served 1 and 2, right? So at this point of time, at the beginning, before C3 arrives, it's C4, C5, C6. Now C3 has a request arriving, so once it arrives, I push it back. Okay. Now I look into the top. C4 already served it, then C5. One very important point here at the end of C4 is that I remove C4 from the queue because I served it, but C4 has another pending request, so I put it back. Okay. So at the end of this slot, it will look like C5, C6, C3, and then C4. The reason I added C4 back is because here C4 has 2 requests. Once you serve the first one, you want also to put it back to serve the second one. Okay. And then C5 is served, so C5 is removed, then C6. Then now I come to C3, and then C4. Okay. Did I do something wrong?
Different from the figure before it. Figure before it said. Okay. One serves C3, then C4, the other C4, then C3. But in your case, both of them are serving C3, then C4.
Yeah, because you remove the request from the queue, and then you, okay, you don't put it back at the end. You do it back once you really remove it. Okay. So what happens in this implementation is we have done something wrong here. So we said at the beginning of C4 slot, I take C4 out of the queue, serve its request, but then put it back immediately. I don't wait until it finishes, right? So you put it back before C3 arrives. So the order will be C4, C5, C6, and then first, and then I take C4 and then put it back at the beginning of the slots at this time. And then afterwards, C3 arrives. So it will be C5, C4, and then C3. Okay. So if I confused you, so what did I do here? At the beginning of this slot, I have C1. So I take C1 out, then serve it. Does C1 have any request? No. So I don't add it back to the queue. C2, same thing. So the point is that cores are removed from the queue at the beginning of the slot, not at the end, right? Then now C4 has a request. So I remove it from the queue and I serve that request. But on the same time, I have another pending request. So I add C4 back immediately. And I do this before C3 arrives, because C3 arrives 2 cycles or 1 cycle after the beginning of the slot. This is why here in this order, C4 is before C3 in the queue. Okay? Not necessarily. That's also an excellent question. This arrival order is something arbitrary. It's something depending on the application. So I gave you the problem like this. I tell you at the beginning, those requests arrive. At time 21, C3 arrives. This is how we formulate the problem, right?
But C4 was the OCP, that's what it.
Exactly. Questions? So now if you look into the service order, you will see that here C4 should really come before C3, right? Because if you look into the order, C3 is before. So this service order is taking C4 first, but this one is taking C3 first, right?
But then, Mr. What's the difference?
Well, in performance, in this example, nothing different at all, right? It's just basically different order, right? Latencies might be different, right? But again, this is just 2 different implementations or flavors of round robin, right? Okay. You see the difference? So again, in an exam, what I might do is give you a sequence of requests arriving at certain times, and I tell you do it round robin, the two versions, TDM or conserving TDM, and the other ones we will see next. Yeah. We will have another answer after we finish all the arbiters. I will give you another problem that we solve. And again, there will be also exercise problems shared with each. Okay. Good.
Is it always the case, like university, that like there's a trade-off between performance and predictability?
Can you say that again?
Is it universally the case that there's always
In high performance embedded systems, yes. That's always the case. Because I want to achieve high performance, and at the same time, I want to maintain timing requirements. Yeah. So now, one thing that is up until now, round robin with its two versions, TDM, work conserving TDM, did not really focus on is assigning different priorities or different service to different tasks, right? So we said they are fair, but on the same time, they are not requirement aware. So this disadvantage is true for TDM and round robin and even work conserving TDM. Like every core gets one slot every round. But what if core one has a task that will require more access, or core one has a task that is more critical, right? So all these arbiters are not requirement aware and are not criticality aware. They don't take into account the importance of the task. Okay, so that's one of the disadvantages. Now, to address this problem, we have an arbiter called priority-based round robin. In priority-based round robin, you assign. Did you hear about priority-based round robin before? Right. So it's round robin with priorities. Yeah.
Yes, we have heard in operating systems.
Yeah, well, I don't
But a
remember.
very short discussion.
Yeah. Yeah, that's okay. You don't remember. He remembers. That's fine. So basically, the key idea is not every core or not every agent for the arbiter gets the same service, right? In one possible implementation, you divide your cores into critical and non-critical, maybe two priority levels. And you start by servicing the ones with higher priority first, and you only serve the ones with lower priority in the other slots, right? So you focus on the importance of the requests. Here, for example, if we let C1 and C2 and C3 to be the critical ones, and 4, 5, 6 are the non-critical cores, then for priority-based round robin, it will be cyclic around only the critical ones, C1 to C3. But what do we do for requests from C4 to 6? You only serve them when the arbiter does not have anything from these cores, right? So that's the key idea. So the way your arbiter will look like is I will have C1, C2, C3, C1, C2, C3, like if this is TDM, for example. Now, what is the advantage of this? If you think about the worst case of any request from C1, what will the worst case be? In this example?
The other important cores like C2 and C3, so it will take like n minus 1.
Yeah, n minus 1 if it's round robin, and n if it's TDM, right? But n for you is only the critical ones, right? Yeah. So in that case, your worst case latency for talking, for example, about priority-based round robin or priority-based TDM, you're talking about the n critical minus 1 multiplied by your s. So you reduced your n from 6 in this example to only 3, right? Because you only consider arbitrating among the critical ones. What is the disadvantage? Yeah, those other non-critical ones, basically, they don't get any guarantees, right? Like they might be scheduled if there is nothing in the system. We call this opportunistic scheduling or best effort or, right? It's on Slack slots, but in reality, there is no timing guarantees for them at all. Yeah, they can start, theoretically, right? So this might work if your system only has two criticality levels, critical and non-critical, important, non-important. But we said in automotive or avionics, you have multiple criticality levels. So now what happens if there is a task in the middle that would require some guarantees, but it's not as critical as the highest critical one? Priority-based round robin doesn't work for it, right? You need something else. Good, but at least it accounts for two levels, and it reduces the worst case of the important ones, right? So if we solve our exact same example from before for priority-based round robin, we'll have something like this. At time 0, again, the same sequence of requests arrive. C1 is my starting point. Does it have something? Yes, so I serve it. C2, I serve it. Now C3 does not have anything. This is the time where I switch from the higher priority ones to the lower priority ones, because none of the C1 or C2 or C3 have any request. So the arbiter can spare time for the non-critical ones. So it served one request from C4. But after it's done, C3 request arrives, so it's being serviced immediately, right? Even if C4 had an earlier request to be served, I don't care. You are non-critical to me, right? Okay.
But it has to let the first C4 finish.
Yeah, because you don't preempt. Most of hardware arbiters, there is no preemption. It's like, unlike operating system schedule. Because I allow one request to the bus, it starts transferring data. It doesn't make any sense to cut it in the middle. You just lose the time and the garbage, right?
So,
Yeah.
for a critical task, your formula is like n critical minus 1 times
Yeah.
this, right? But for non-critical.
For non-critical, no bound.
zero.
Yeah, well, 0 means you finish in no time. In
Sorry,
reality, it's infinite,
infinite, but-
right? Yeah, theoretically infinite, that's correct. So there is no bound. You have a question? Yeah.
E1 and E3 enter the conjugate.
At the beginning here,
Yeah, which one will be?
or you mean here, like after C1, C4 is served, like basically any time before this time, if any request from C1 or C2 or C3 arrives, C4 will not be serviced because C4 is non-critical. The only reason C4 started is that I see your questions. What if, for example, at this point of time, C1 also has something arrived, right? So in this one, we're talking about which implementation of round robin. If we're talking about round robin that pushes in cores to the queue only upon their arrival, then we see which one arrived first. Because at the beginning, you have C1 and then C2, C3 did not arrive at all. So these ones get serviced at the end here. None of C1 and C2 or C3 have anything, but then C1, C3 arrives. So if C3 arrives first, it will be top. If C1 arrives first, it will be top. Yeah. Any other question? Okay. Good. Then to move from these two levels to multi-levels, we do something called weighted round robin. Did you hear about WRR, weighted round robin? So we start assigning different weights. Round robin baseline is fair. Everyone gets only one slot. But that's not necessarily the case. You can really assign 2 slots or 2 rounds or 2 entities in 1 round for core 1, 3 for core 2, depending on the requirements, right? So the way weighted round robin really work is that, say, over the round of a schedule, over the cycle, it's not necessarily that every core gets only one chance. Maybe core 1 gets more chances than core 2 because it requires more access, right? So it starts putting weights, right? In this example, I'm making C1 have a weight of 2. So I grant C1 2 accesses during 1 round, C2 2 accesses during 1 round, and everyone else just 1 access. Okay? What is good about this thing is that C1, whoever gets more weight, has better performance, right? Because I get to finish more requests within 1 round. What is the disadvantage? It's not fair, yeah, for sure. Yeah. Well, but here, unlike the priority-based round robin, everyone still gets a chance, right? Once, and this is maybe a good point to highlight this. A starvation will happen if you don't get any guaranteed chance. Any arbiter that gives every core a guaranteed chance, even if it's very little, you don't starve because you get a chance. Yeah. Yeah, that's arbitrarily. It depends on you. You look into your program and you say C1, for example, want to access the bus more. Then I give it more weight, right? So this is a design decision, right?
So it's not basic.
Yeah, this is based on requirements more than criticality. Yeah, that's one of the disadvantages. That's correct. But there is another disadvantage that if you look into the worst case, and maybe we will conclude with this observation, the worst case of requests from C1, did it improve by giving it more weights? Again, hopefully you learn now from last lecture, how do we drive a worst case? I want to look into the worst case arrival time, the instance, to wait for the maximum time, right? So that's what we call a worst case. Now, what is the time in instance that a request from core 1 arrives such that it waits maximum?
When it comes in the execution of C2, just 1 cycle after it starts,
What about it arrives here, as we said earlier,
that can work.
right?
It's
Because
an additional request.
yeah, so in that case, if I arrive here, I have to wait for 1, 2, 3, 4, 5, 6, 7 slots. In normal round robin, how much do they have to wait for? 6. So in reality, your worst case increases, does not decrease, right? So weighted round robin does not help with predictability, does not happen with worst case. It helps with performance, right? With average case performance. Okay? Because the worst case is the time you arrive such that you suffer the maximum latency, in fact, increased. Okay? So let's stop here and we continue next time. Thank you.
These slides, already you have cited some papers from different people. Like how they may have introduced these, obviously, these
Arbiters,
arbiters. But then how do they like, is there a standard to measure the performance or the?
Yeah, measure predictability is done through analysis. Measuring performance is running experiments.